next speaker, Werner Zellinger, who I know for many years now, also has his roots, at least in his study also in arts and technical mathematics at the University of the Arts, and then he came to Linz and also to SCCH, where he was part of the research team. And in the meanwhile, he is member staff of the Austrian Academy of Sciences of BICAM, the Institute for Computational Mathematics. So, and now mathematics, that's the topic. So, welcome.
Thank you very much, Bernhard, for the introduction. We heard today the rabbit hole of AI at the beginning. So for me, mathematics is an orientation. Mathematics is an orientation also what did we do, what have we for sure as a knowledge. So my slides are prepared in German. If something is not understandable, please just ask. But I will not talk about vector matrix multiplications, what we saw today a lot. I will talk about how we can formulate learning, how we make statements in statistical learning theory, and what can we learn from this, and for what can we use it to produce new algorithms. My background is, as Bernhard said, in the industrial side, and I always enjoyed to study the mathematical basis of machine learning to have an orientation. Only a short glimpse on Austrian Academy of Sciences. It's founded in 1847 as a basic research organization. There are around 1,800 employees. The Johann Radl Institute for Computational and Applied Mathematics was founded 20 years ago to do basic research in applied mathematics. We have around 50 people, and I'm in the group of inverse problems in mathematical imaging, where we also have the part of studying learning as an inverse problem. My personal research interest is so-called adaptive machine learning. We have as a goal to reuse data and models which have learned before to improve the learning on new things. Of course, this is to overcome data limitations, like we have two less labels or annotations of data, or we have two less data at all. And the key challenge is distribution shift, which means that new data can origin or can have statistical characteristics which are not the same as the data we had before. So something changes in the environment or so, and then we have problems in the original assumptions of learning. I want to give an example here. It originates from a project that is actually from Bernhard Moser as research director of SCCH, but I stole it here because it's really a beautiful project for me to see how fast basic research can nowadays go to applications. And the project was to detect defects on friction materials together with the company Miba. And in earlier, so 30 years ago or so, we would have learned one model for each friction material. But this gives us problems if Miba wants to produce a new part and we don't have a lot of data from this new part. So what to do? We want to use the older knowledge from the older defects, from the older parts, to learn a model on all these friction materials, and how to do is the goal of the direction of the machine learning. My talk will be structured in three parts. The first are about two specific mathematical challenges we have in KI: reliability and customizability. Then I will do the mathematics. I will give some definitions. Also, I will define what is the problem of learning from the view of mathematics. I will give the definition of a learning algorithm from the mathematical, with the mathematical classes always. And we will manage to see a first theorem and even sketch the proof of the no free lunch theorem. At the end, I will show you recent advances in reliable adaptive machine learning. So, maybe we have seen this guy, Sam Altman, the CEO from OpenAI, which produced ChatGPT, and he talks about the key milestones in AI development and denotes reliability and customizability as two specific key milestones. But this is not only Sam Altman saying this, so if we look at this recent review article, Scientific Discovery in the Age of Artificial Intelligence, published last year in Nature of a lot of machine learning experts, they define distribution shift even at the beginning, and they say a question of out-of-distribution generalization, which means that the machine learning model works on future data that is not of the same characteristics as we had before, so exactly what we said before, is at the frontier of AI research. And this will be part of the talk. So customizability is not only with respect to linear friction materials. You can find it also when, for example, you have a manufacturing machine and you sell this manufacturing machine and the customers change some work pieces or some settings of these machines. Then sensory data shifts, changes, and the machine needs to be recalibrated. The learning models need to adapt to this new situation. We also see this in some of our medical projects with our partners of Medical University of Innsbruck, where we wanted to learn a stenosis detector on the vertebral arteries, but the doctors only annotated the cerebral artery, and they are different, so the measurements look different. So we see this very often, and now, Bernhard, sorry to put bananas in the project of me, but from the point of view of a researcher, we want to ask ourselves, how far can we go? So can we learn from any data, any other data? Can we use the data of bananas to learn a defect detector for friction materials? Can we do that? I mean, the question is not so unusual, because many people use pre-trained neural networks that are trained to differentiate between cats and dogs to learn defect detectors for industry. So I will spoil a little bit here. This slide is actually a summary of the next 10 minutes, so if you don't like this slide, maybe now make a break and give me another chance in 10 minutes or so. I will define, from a mathematical point of view, we first need to ask ourselves, where's the data from? We need a model of the reality. And usually in statistical learning theory, we say the data generating model has two parts. One part is an unknown function, which we want to approximate, and it has some statistical probability part. This is that we say that the measurements come with some error. And I will call this P. For those with mathematical background, P is a probability measure on some compact input space. And what is learning now? We have our model, our data generating model, and we ask ourselves what is learning. And learning has been formulated to be the problem of given some data. We want to find an unknown dependency, the F, which is from the data model, but we don't know A, with a small error on new data from the future. This has been formulated to be learning. There are some other definitions of learning, but this is one of the most accepted ones. And now we are in a mathematical setting. We have a data generating model. We have defined our problem. Now we can make statements about the problem. And we can make statements about what should we do. And what we do is actually will lead us to the definition of an algorithm. An algorithm for us takes the data, which comes from P, but we don't know P, and gives us back this function, or some similar function. This is an algorithm. It's even a mathematical object, it's an operator. It takes data sets and gives us functions. Now we are in a setting that is kind of, we found our orientation, at least with mathematical classes in the rabbit hole. We are back in approximation theory and probability theory, and we cannot do everything with what has been discovered in mathematics. And this I will now do. So let me precisely again talk about these three parts. The data generation model. How can we imagine it? It was kind of abstract, probability measure. We have given our data that comes from our data generation model. We can imagine it with two axes. We have given x, y pairs, right? And the function, which is f, goes through it, and the points originate with some probability a little bit far from this function. So we put the normal distribution here around the regression function, base predicted, sometimes called, and then we draw the data. And what is very important here is that we don't know p in reality. Maybe sometimes if we have observations from some planets or so, we know some good guesses for p. But do we know good guesses for the underlying function of text? What should we predict as the next word? ChatGPT is trained as a model that takes some text embedded in some space, x, y, and it predicts the next word. So we really don't know. The problem of learning is now we have given these data points, and for a new x, we want to find the point y, so we want to find a function which tells us which of these 3 points to choose. Right? If a new point arises, for example, a new word, or a new position of a planet, we want to know where exactly it is. So, and an algorithm first has to make some decisions. We have to decide of which form is our function. Here, for example, it's a line. We learned that the line can be formulated as kx plus b in school, and it has two parameters, the k and b, and the learning algorithm, for example, takes the data and learns this k and the b. And one of the famous learning algorithms, also given in the introduction of this famous deep learning book, is to fit the line and compute this k and b such that all these distances to the points is minimum. Okay? The point is that we make an error also with our decision, right? If we say, okay, we want to think about linear models like this line, but in reality, it's a part of an ellipse, then we make an error. And nobody tells us if this is an ellipse or not. This will always depend on our assumption. We saw this algorithm, guess when it's founded, so when did we find this algorithm? Any guesses? Some interaction? Yes, please. Johannes Keppler. No, very good. It's very good because Johannes Keppler founded that we have ellipses, right, and not circles. But Johannes Keppler did not think about a rigorous description of the error. It was discovered later because in this algorithm the error parts play a central role, right? But Johannes Keppler is very good. In fact, the guy who invented this algorithm also used the ellipse founding of Keppler. And what I think is interesting, that the guy who founded this algorithm said an opinion had universally prevailed that the complete determination from observations and tracing a short interval of time was impossible. An ill-founded opinion. So at this position of history, mathematicians thought that if you have some observations from a planet, you cannot predict the next position. And this is exactly the problem setting of learning. So at this stage, without any computer, we had exactly a learning problem. And this guy solved the learning problem and proposed an algorithm and even gave some guarantees. It was carved with Gauss. It was published in Theoria Motus Corporum Celestium in 1809. Here are these observations and also the planets. Even what Gauss did, if you look carefully at what he wrote, he selected 3 observations which fit well, and then he fitted the circles. So there was a lot of engineering also involved. But the learning algorithm is not only if we want to predict the next position of the planet. It's also we can embed, as I said, text into coordinates, and we can embed words like how old is Carl Friedrich Gauss. And the next point is predicted by ChatGPT, and it tells us that he is not alive anymore. But okay, what has this to do now with our, I mean, we live not 100 years ago, what has this to do with reliability and customizability? A very famous theorem in machine learning is the no-free lunch theorem. And actually we can prove it now with what we thought about. The theorem says that no algorithm which takes the dataset and returns the functions has a small error for all our models. That means more. It means that our guarantees on the expectation always depends on our assumptions, on the mathematical assumptions we make. I think we have another session to discuss the implications of this. The proof is like that. Imagine we have a line, then this line may be a good predictor for the unknown ellipse. But if the proof P is this polynomial, which by the way exactly produces the data, so we don't know if it's an ellipse. Maybe for a planet we know that it's an ellipse, and we don't have a planet which jumps around in our universe. But for many other things like text, we don't know. And if we select a line, and it's not the ellipse, but it's a polynomial, then we have a large error in the future. And this needs to come from, we need to have some models about our underlying learning problem. Okay, usually mathematicians, which I will not do now, but usually mathematicians do not make assumptions on the single line, but make assumptions on the properties of this line. Like we say we don't know exactly if it's an ellipse, but it's something similar like an ellipse, or it's quite smooth function. And then we can make predictions, like say, okay, if we have 1 million of data points with high expectation, we have a small error. This kind of predictions exist. Now let me give only some slides. So I told you the whole model of mathematics, and now I will tell you that none of these applications satisfies the assumptions. Why? So we need some adaptation here, and this is exactly what adaptive machine learning tries to do, and research about adaptive machine learning, that in practice we have here different underlying models, different distributions. So we have different characteristics of a new machine part, and we don't have only one single P. And again, back to the question, can we use bananas to predict defects on the future material? Well, it's a question of distance. Somehow we have intuition that it's like that, but we can precisely state it. This, on the left-hand side, is the expectation. So what we can expect in the future if some xy point is drawn from a different model Q. So all this outside means what can we expect from the future? Of our error. So this fx minus y is exactly this error, right? So what can we expect for our model from the future is what we can expect, how well it works on the bananas, plus a distance between P and Q. Now, well, this is just a formulation of what we think it is, but it is more because we have here a precise distance. We can sample this, we can analyze it, we can compute it. We can, for example, take the bananas, put them into some generative model, transform it that it looks similar to friction materials, And this we can check by the distance, and if the distance is small, we use our big data of bananas to compute a learning model on the friction materials. And this is how algorithms in this direction work, in an abstract sense. Another approach to this problem is, for example, we use the idea of calculated Gauss. It's not bananas and friction materials here, it's more a data set from the internet, so the goal is to make a security system for airplanes and see differences in objects. And the problem is we don't have a lot of data here, but we have a lot of simulated data. So what we can do is we can train a good model on the simulated data and a very bad model on the not simulated data. We use what Gauss discovered and combine the models to an F that uses both information. And the goal, the tricky thing here is that the error we want to minimize, so the expectation of this new model of the difference cannot well computed because we don't have data here. And the question is how to solve. And again, it brings us back to mathematics, it brings us back to Austria, it brings us back to Johann Radon. By chance, we like him at Johann Radon Institute, of course. And you can see that this expectation as a mathematical object, this is similar to a norm, can be expressed. So this we want to minimize, but we don't have a lot of data. Is the same as the data here. So now we do a similar thing as the inequality with the distance. The error about the data we have from this we have a lot of data, plus some term disappeared here. It's this object is called radon-nicotine derivative. Thanks to Johann Radon, we know a lot about it. We know how to compute this. And we can estimate the whole thing, so we can actually, this enables us to work on the simulated data, not on the real data. Just use the real data for estimating the radon-nicotine derivative. And this we know to do. Why do I say this? So this we used a lot, and there are these big machine learning conferences, and they do big advertisement from our own side. It was selected as one of the main, as one of the top 5% machine learning works in one of these most free conferences. But it goes back to Vienna, it goes back here, and with these words maybe I give, there is enough all around, maybe I give back to Bernhard. Thank you very much.
I think this was not an easy job. To give insight so deep into the mathematical backgrounds of artificial intelligence and machine learning. So thanks a lot to Werner. And also, it's another example of, let's say, top science in Austria. As mentioned, this outstanding publication at one of the top conferences worldwide. Okay. So, the next speaker comes from a different direction. Yeah? So now we have heard something about the neuroscience, what is new about the mathematics, so to see how sophisticated and various all this is. And the next speaker will come from VWGÖ, Werner is the Wirtschaftsuniversität in Vienna, and he is working in the group of Sabou and Moser, looking at knowledge modeling, and this bridges what you have heard, the machine learning part, statistic part, with knowledge. Okay, so thank you.
Thank you. So, dear symposium organizers, distinguished guests, and fellow speakers, good morning. My name is Moser. I'm coming from the System Research Group, the Institute of Data Process and Knowledge Management, VWGÖ Vienna, and I'm very honored to be here today to talk about the topic of Neuro-Symbolic AI. Our great speakers already discussed several topics related to AI from different perspectives. Professor Linz discussed about the neuroscience view of using our brains as the role model, while Professor Zellinger explained the role of mathematics in AI. The goal of my presentation here is to share an insight about AI from another perspective, grounded from the psychology point of view. On this matter, we would like to borrow the intuition from the theory of thinking fast and slow from the late Professor Daniel Kahneman, a great scientist and a Nobel Prize winner who unfortunately passed away a few months ago. His theory stated that the human brains implement two distinct mechanisms for reasoning for decision, which he called System 1, that represent human intuition and instinct, and System 2, that represent this rational thinking. This system works in different, almost contrasting manner. For example, System 1 allows us to respond fast to certain situations, but it is error-prone, while System 2 needs time to process certain situations to come to a decision, but with more reliable result. System 1 operates unconsciously, often based on similarities or habits that we already have, while System 2 needs time to process the situation. Takes conscious effort to go through the decision tree and look for possible outcomes and decide based on human logic. If you compare this to for example, driving a vehicle, System 1 would be similar to autopilot, while the System 2 more on the manual control of your vehicle. A simple example of this System 1, for example, is when you're detecting hostility in a voice. I mean, for me, it's worked pretty well, especially when I detect this hostility in my wife's voice, for example. And System 2 is typically used when you're trying to tell someone your phone number. You try to remember the sequence of the number exactly and tell that to the other people. On his book, Professor Kahneman described that we use System 1 a lot more than System 2. Roughly about 95% of our decision came from the System 1, compared to about 5% that came from System 2. However, they are both important since they are serving different purposes for us. Interestingly, these two systems are remarkably similar to the two main branches of AI. The first branch, the sub-symbolic AI approach, is based on pattern recognition from existing data, which is operates similar to System 1, while the second branch, the symbolic AI, operates and reasons based on explicit representation of knowledge and logic, which is closely resembles the rational thinking of System 2. Such resemblance between these two systems of our thinking has become one of the inspiration toward this new wave of what's so-called Neuro-Symbolic AI research that combines techniques from both sub-symbolic and symbolic AI. To understand their similarity further, we will first look at how sub-symbolic AI approach resembles System 1. One of the typical tasks that addressed by the System 1 is characters or number recognition. Therefore, I wanted to try to make this a bit more interactive and try this following exercise together with all of you. Try to use just the System 1 sense like responding instinctively and not to trigger the logical part of your brain. So exercise this. Could you please your hand if you think that this character is a 2? Okay, thank you. Yes, this is a 2 based on the data that we have. How about this one? Who thinks that this is a 2? Okay, just 1, 2, not more. Okay, Well, this is also a tool. So depending on where you live and how you learn how to write, well, some people think that this is also a tool. Next one, how about this one? Who thinks this is a tool? Okay, 1, 2, 3, 4%, okay, 5. Well, actually, this is not a 2. This is a 1. Okay? The last one, the hardest one. How about this? Who thinks that this is a 2? Oh, actually, it's a lot more than the previous one. Yes, this is actually also a 2. This is written by one of our family members due to this condition of dyslexia. He has this issue of separating direction of characters. So he wrote down to sometimes he also do it the other way around. So his system 1 actually believes that this is a 2. Okay, so with this exercise we now show our capability of system 1. And what I want to say is that advances in AI research shows that neural network, one popular approach of subsymbolic AI, can already mimic this ability by learning patterns from large amount of data. For example, Nielsen, in this link, explain and demonstrate the example approach of using a large collection of a number handwriting to train a neural network to do this number recognition. On this case, we split up the number into 28 times 28 pixels, input and train classifier to recognize the character from 0 to 9. Further, due to the recent advance in the hardware technology, it facilitates the rapid growth of the deep learning network approach, which is another class of machine learning methods that learn multiple levels of representation corresponding to different layers of a processing unit for feature extraction and transformation. In this example, the deep learning network is used for classification tasks of the image, and based on various exact feature of the image, eyes, nose, mouth, and so on, and then decide that this is a tab, rather cute tab. Another popular example of this subsymbolic AI is this large language model, of course. Everybody knows to talk about it. This is something that's really popular at the moment, which is actually also represent a class of deep learning architecture which is called transformer. There's a neural network that learns context and meaning by tracking the relationship in sequential data such as working sentences. GPT is one example of such a family of large language models that is by OpenAI, and ChatGPT is actually an application, a chatbot that built on top of these GPT models. Various other alternatives have been created and developed both by industry and academia, including, for example, Llama with Meta, this DLM, not sure whether you know this is coming from Symphony University. There is also this Cloud by Anthropic and Gemini from Moser, and many others. However, despite all of this development and successful usage in many tasks, it still has a number of issues such as hallucination and transparencies. I'm not sure whether you can read this. It's too small. It's okay. So this question is like I'm asking ChatGPT just a few days ago, who are the members of my semantic system research group at VWGÖ Vienna? Let's try this. Well, it shows our answer. I know Sabrina and Axel. I work a lot together with them with VWGÖ, but they are not part of the fact they are not part of our semantic system group. We are in the same department, we are working together, but they are not in the same group. So this information is being provided to us by this to show that there is still some issues with hallucination, transparency of how they get into this result. This makes you sound familiar. Not with the AI, with the human. So when you ask somebody actually to answer some question that they are not familiar with, sometimes we do hallucinate in the sense that we are giving answer that is not 100% correct, just based on our intuition. In that case, sometimes people switch to their system to and try to think from the logical point of view and try to reason whether we can give some answer or decide not to do it because we don't know about the topic. Okay, so far we already provided several examples of the sub-symbolic AI system and show how they resemble our system 1. How about the symbolic AI system? In the next slide, we will look at a few examples of those systems and their resemblance to system 2. Many people have been using applications supported by symbolic AI technologies for years without realizing it. One prominent example is this Google search engine. From 2012, Google launched the Google Knowledge Graph to help their users to discover information in a more efficient manner. For example, our search of Peru, Vienna, in addition to giving all the answers as a list, it also provided an info box on the right side with some of the facts about Peru, Vienna. This is provided by this Google Knowledge Graph that they have inside. This information can be then represented in a single graph, where Vienna is a central node and all the information related to its properties as well as relation to other objects. Such knowledge graphs are structured based on ontologies, typically expressed in some formal, logic-based symbolic language to represent concept, relation, properties, and rules of knowledge. Knowledge graph can contain lots and its million and billion of facts. In case of Google Knowledge Graph, when they launched it in 2012, the initial version consisted of more than 500 million objects with more than 3.5 million facts and relation between this object, similar to the one that you see here in the slide. Another popular symbolic AI resource is Wikipedia, an openly accessible knowledge graph, originally developed from an academic project that automatically extracts structured information from Wikipedia and then into its structured representation. In the provided example here, probably this is not okay. We are extracting, in Wikipedia, they extract information from the Beatles page in Wikipedia and transform it into knowledge graph where you can access it through this web page of the Beatles. In a simplified graph representation, again, you can see how the information is structured, what kind of relation it has, and its property of this. For example, the hometown of the Beatles, who are the former band member, and so on and so forth. While both examples that I provided only show a simple knowledge structure, symbolic AI allows users to represent complex knowledge representation to facilitate logical reasoning and querying on the underlying knowledge structure, similar to the system 1 of human brain. However, while it facilitates this reasoning capabilities, symbolic AI approach also has some limitations, such as the limited access to learn from existing data and a large amount of resources necessary to address this incompleteness of knowledge. Okay, we already looked into examples from each sub-symbolic and symbolic AI with some of their advantages and drawbacks. For example, this symbolic AI holds advantage in terms of transparency. You can really look into the data because it's explicitly provided. In contrast to the parametric knowledge contained within sub-symbolic AI. On the other hand, sub-symbolic AI holds the advantage that it can learn patterns from data, which is something that symbolic AI is capable to do. In the attempt to address this drawback, in the last few years, like I already said before, that this terms Neuro-Symbolic AI that combines two branches of AI is becoming more popular. And we will next provide you with two examples of this Neuro-Symbolic AI approach addressing different goals, trying to address this issue with each of them. The first example of the Neuro-Symbolic AI system is knowledge completion. Knowledge graph, we already said before, can contain linear of entities and billion of facts. But despite of its size, it is well known that even the richest knowledge graph suffer from incompleteness. For example, 3 days, which is the basis of the Google knowledge graph before they bought it into their company, over 70% of person entities contained within 3 days doesn't have information about the date of birth, place of birth. Even further, 99% of the person entities didn't contain information about the ethnicities. So this kind of information is missing from the data. To tackle the challenge, commonly known as the knowledge composition, we can use neural network approach. For example, we can have a number of instances of persons that are or were living in Austria and has Austrian nationality. For example, Mr. Werner here and Mrs. Zellinger are Austrian and live in Austria, and with all the additional properties and relations that it has within the knowledge graph. But then we have other people, less known people like my colleague Gregor here, that also live in Austria and has several similarities to the person that actually have the Austrian nationality. And we can use the techniques from subsequent AI, such as graph-embedded neural network, to try to infer whether Gregor also has the Austrian nationality, like this. And by the way, yes, Gregor is Austrian. In real-life scenario, this approach has been used in various domains to help with many tasks. One example that I provided here is coming from Zellinger in 2021, when they tried to use the knowledge completion techniques as a way to identify possible drugs for COVID-19. The second example of Neuro-Symbolic AI system is this retrieval augmented generation. And I don't know about you, but I have, every time I open LinkedIn, at least I see a few articles mentioning this one. And this approach combines the use of knowledge-based and large language model, especially to improve the performance of the LLMs. Is a technique that combines information retrieval with text generation, allowing the AI model to retrieve relevant information from certain knowledge base that they are using and then incorporate it to the generated text. And this right before LLM to actually leverage external knowledge to improve the performance. So, I wanted to illustrate a simple RAG approach. Let's go back to the previous LLM example, where we actually asked LLM ChatGPT about the member of semantic system research group of VWGÖ. If we already have a well-curated knowledge graph or knowledge base in that data about the topic that we have here about our group, we can utilize RAG by performing data retrieval from the knowledge graph and then use it to enhance the problem that you use, like this, to get the correct result from the LLM. This is to address the issue with the hallucination that we had earlier, because we have a source of data that we can rely on and we use it then to augment the text generation, as you see here. And by the way, all of this information in the knowledge graph is correct. So this is all our group members led by Professor Marta, Sabou. Okay. So, as a summary, in this topic, we have discussed two different AI approaches and drawing their parallel to the two systems of the human thinking. The sub-symbolic AI, which resembles the system one that's representing human intuition and instinct, while the symbolic AI that resembles our rational thinking. We also have shown the example combination of these two systems to address the limitation of each individual solution, showing the importance of this combined approach. To this end, I personally believe that similar to how these two systems of thinking form our complete reasoning system, that the future of AI also hinges on the combination of these two branches which often dubbed as Neuro-Symbolic AI. Finally, we are excited that VWGÖ will become one of the partners of this bilateral artificial intelligence project, an FWF excellent cluster led by Professor Hagenberg from Linz, and will be started in October this year in cooperation with several foreign universities and this institution. Some of you actually already here. Where the project will focus on the topic of bridging the sub-symbolic and symbolic AI approach and contribute to shape up the future of AI in Austria. With this, I conclude my talk and thank you.
Okay, so may I ask Werner and Robert to come to the stage? If I can, please. Okay, so, and this is now also the opportunity for you to put questions or even to come take one of the seats and okay. Yeah. So I would start to ask you. So now this was a very, let's say, more tough presentations about the fundamentals, about mathematics, about the neuroscience background, and then some outlook into bridging. Or imitating what is going on in our brain, system 1, system 2. Okay. So are there any questions? Yeah, okay. Sorry.
My question.
That's my picture. Let's change.
Thank you so much. So my question would go to Dr. Zellinger, a small one and a practical one. You said that we need to have a very small distance for the error between, let's put it like in your formula, between P and Q. Who decides, or at which point of time, can we decide that it is small enough? And who decides that it is small?
Okay. Yeah, it's great.
Thank you for the question. It's a very good question because I like the distance question. Actually, the distance between two samples is a fundamental question of statistics. So, how to calculate this distance is a statistical test. And when a statistical test is such that we like it, has been answered in statistics by confidence values, p-values, and so on. On the other hand, in some applications where we have more knowledge, like for example in this friction material application, we had an independent data set where we had some new friction materials which we did not touch in learning. We calculated somehow the performance of our statistic there, and then we made some decisions based on practical considerations like we have a probability of 90% of error, and this is okay for us. This is a decision made by the company. So on the mathematical side, I would say the answer is given by statistical tests. On the application side, I would say the company can decide. Did this answer your questions? Otherwise, we can drink the coffee later. It's a fundamental statistical question, so we can talk the whole day about it. Thank you.
Okay.
Concerning the Model 2 in the last presentation, as far if I understand it correctly, so your conclusion is that you take straight connections, or strong connections out of the given data. But how does the system get these strong connections out of non-formatted data?
Mm-hmm.
Thank you for the question. In here, I mean, indeed, a lot of research have tried to extract this kind of information out of unstructured data. As you see earlier, like the use of this system 1 to help with such kind of extraction will be really important. So, so far, I mean, if you do it, when we do these things, I mean, in practice, actually, oftentimes we're reusing the techniques from system 1 to actually help with that. Thank you.
Maybe to add, so particularly as one of our projects, we're facing the problem that the knowledge graphs are getting so large and so large, and then it's the question how to do exactly this, to generate it, and to populate it, to fill it with data, and there are also generative AI helps. Also because with this method you can also generate structured data. You can structure it. You can even generate code, and you can also generate knowledge graph structures. Okay, further questions? Okay.
The next one would be for Professor Lebenstein. So, how far is your time and energy efficient, let's say, brain model based, so if you mind technical terms, from practical application? I think the last one you showed us is the complicated. One was the elephant trunk-like, and the other one was the robotic arm. How far is the future when we can see it applied?
Right. So in principle, I'm doing basic research, so I'm not so much interested in applications. But to get applications, of course, one has to implement it first in pseudo hardware, which we also don't do, but some partners did that. And of course, we check what you can do with it, and we're thinking currently about actually with some partners also to start to go into the direction of building real applications for them. One advantage of the systems is we don't talk about large systems, but rather relatively slow systems, but they can be extremely efficient. So they can run basically, forever really on very low power. So they can be used, for example, as sensors for different things, so currently we don't really have an application, but we are going in this direction right now.
Okay, keep up. But we have some plans. Yeah, maybe you can mention it.
Sorry?
Maybe you can mention this, our plans for the future.
Our future plans, yeah.
Bernhard.
You know this better.
Okay. So maybe So together with Robert and some colleagues in Linz and also SCCH, we have some plans based on these principles to have some applications in mind for environmental monitoring. Think of full root, forests, with smart sensors, looking like a beetle, and they can measure humidity and other things, and temperature, also to measure how the growth of the trees, and this can be combined with satellite data. And this is the purpose of this is to have it energy autark, so without any maintenance. And this is just an example. We can also apply this approach for other environmental monitoring applications. But it's, as Robert said, the starting point is with sensors, make them smart, so that they not all the time are reporting or doing some communication, because this also costs a lot of energy, but only in some when it's relevant. And this is at the local point of view of the sensor, but then you also have the communication part, and this all this to based on these principles. And by the way, there's a lot of mathematics also behind. Other questions?
Yes, I have a question on all things. The criticism is that all this technology behind LLMs are based on stochastic, on statistic, and there's the stochastic parrot. People say it's just a parrot, and it can recognize the world, it can understand the world. So, and that's what I learned is that this technology behind these LLMs is not able to understand the world anyway. So, are there any other thoughts and technologies being worked upon on developing other approaches on how to build artificial intelligence so that they can understand things?
Okay. That's a very fundamental question. Maybe also already philosophical question. What is understanding? So, who of you wants to answer?
I can say a few words about it. I think you're right. I mean, first of all, yes, as Bernhard said, it's hard to define what understanding means, but I think you're right. So, we heard the talk before, right? The system 1 and system 2, thinking fast and slow. So I think that this LLM technology is a fast thinking system. So it's actually not thinking, it's just like reacting basically. So the thinking is missing. In that sense, it's very different from how the brain works, at least the slow system works. So of course people are thinking about how we can improve that, right? And this project, which has been years of the Bilateral AI project, actually exactly tries to do this. So we want to combine this fast system, neural networks, deep learning things, with systems which are more structured, where you can have inference, like logical inference and stuff like this. And with this, get a system that is much more closer to the way what human intelligence is. So, I mean, but I think this is really a question on which most people are like interested now and trying to improve in this direction.
I don't know what understanding means. I used ChatGPT yesterday to implement the Jacobian matrix from an optimization solver. So I said should be write down the formula of empirical risk minimization. Then I said I have some special loss function, should write it down. It had some bug, thought it has a different, and then I asked to write it down in Python and it worked. So I mean, in 3 minutes. And the same question I give in my exams. So ChatGPT was roughly 70% right, also the students. So I give the question back, how can I teach my students to understand this?
Okay.
Yes,
Okay.
Just want to say something about that. I mean, most of the answer already given by the other speaker. But just one thing is that it's actually quite intriguing. I mean, like, because there are many ways that this two systems actually interact. And one way is what happens in our brains. For example, Professor Kahneman says that system 1 never shut down. Like, it's always work. While the system 2 is standby. In case the system 1 didn't understand something, they take it over and then do this logic thinking behind it. I was questioning myself when I read this, whether is this like the future or it actually can be like other kind of combination. It's probably not 100% the same the brain work. Probably it's not possible to replicate that. But to find the sweet spot where these two systems can cooperate in the how to say, in the complementary manner would be, at least from my personal opinion, is a key.
Okay.
Here.
Any questions?
Here, I have a question to the last speaker. From the user perspective, and you mentioned hallucinations, and sometimes I also check ChatGPT or Gemini, and then the answer is wrong, but it's not given that the system is not so sure about the answer. But of course, there is a confidence level. The system knows, or the algorithm somehow knows that it's likely or not so likely. But as a user, you don't see any reflection of that. Always in the end, there's a sentence, you should double check, yeah, that I know. Still gives the wrong names of your group without the word that the human being would say, I'm not so sure, but maybe that professor's pass. You know this, I'm not so sure, so how to change that?
Honestly, I'm not sure. Like, but I mean, later on, probably in the future, that where you can. I mean, I try to imagine myself in the same position when I'm asked about, for example, the group of Professor Legenstein, like the name of the members. I won't be able to answer that, right? I can probably try to think about what are the typical Austrian names and try to list 10 of them, probably I get one correct. But typically as a human, you can say that, sorry, I don't know, or like I have about 50% probability that I think it's correct or not. But this can be applied in many ways. I think in the application level, in ChatGPT, you can have this mechanism to tell people actually that they are not sure about it. I don't know.
Yeah, but it's some remark on this, but it's interesting. Yeah, so it's about probabilities and so on. Okay, but actually, with probabilities, with statistics, you cannot express ignorance. If you don't know it, it cannot be expressed by some statistics. It's not the language for this. Yeah? So it also shows that it needs much more what we have in our epistemological reasoning. But there are other questions already also.
Yeah,
please.
I wanted to come back to 70% of students getting the answers right, as does ChatGPT. Maybe they're both just reproducing something and not understanding both. Which would be okay if it's a bachelor program, and a master program might be rather taken back.
So it's not just reproducing.
Was this a question? Because I have your opinion, right? That is not.
My question about the I in the app. It's artificial, that's okay. I think we're all consent on that. But is it intelligent? Is it really intelligent, the I on the AI? Or does it just reproduce probabilistic values? Sorry.
So, from my point of view, I have a very straight mathematical statistical point of view. So these kind of tools like ChatGPT just find pattern in data, and they just solve a given objective by some ansatz in some optimization algorithm. I don't have any definition of intelligence. If you tell me one, I can maybe say if it fits or not. But I also did not read about definitions of intelligence. What we can define is learning. Learning has been defined, I showed it today by Stephen Smale. He won the Fields Medal in mathematics, so I believe he's an intelligent guy, and he defined it that given some data independently drawn from some distribution, learning is to recover an unknown dependency, and we can give some guarantees on that, like say, if the data converges to infinity, we know that we have recovered exactly. And we can also say with high probability, with this and this many data, we can recover this and this function parts. So this is possible, and it helps in a lot of ways, and this kind of mathematics help obviously to find good programs which help us in different practical tasks, like writing down exams for students, for example, which I don't
Okay, so many questions. Please.
Yeah, another question I would like to provide an answer to some of those asked before. I would fully agree that the large language model doesn't have any understanding because it's just trained on language. It's like a very clever parrot being able to reproduce language. Apparently for passing medical tests that's sufficient for many other things, but we cannot really say it understands. Somebody asked, what's the next development? In my opinion, it doesn't understand because it doesn't have what in the 1990s we called grounding. It cannot map any of the words like tour or table or whatever to any physical experience, and that I think is essential for understanding. Now, but we see we don't just have language models, we already have multiple language models that also work with images or other types of input. As soon as we connect them with robotics or something, we will get closer and closer to such groundings, and I think then they will come closer and closer to really understanding what's behind the word. So that's just my 10 cents worth to that. You might comment on that.
Okay, and by the way, this was Georg Dorfner from the Medical University of Vienna, and also member of the board of ASAI. Further questions or comments? Okay, then Camille, please. Listen.
Yeah, thank you for your presentations. You mentioned drug impulse of COVID, for example, in publication. How do I know what kind of data go into the artificial intelligence program that will then generate this output? Are only serious scientific publications being used, or is it also Donald Trump saying we should use Clorox?
What I can say is that this current EU AI Act trying to ensure that you have such information provided, especially when you are dealing with the high-risk system. In our group, we have also institutes that are trying to focus on auditability of such a system in the sense that you wanted to be able to record information about which data is being used, what kind of processing the data that you have, how are the licenses, and then things that happens inside. But this is just not us. A lot of people actually try to do so. To some extent, this is already rectified by the development of data models such as Google Model Cards, where it tries to provide some basic information at least, who's model creator, what kind of training data is being used, how the iteration processes. The thing is that we observed that model cards, I think it's created in 2021, I forgot exactly, already for a few years, and it's implemented, for example, in the Hagenberg platform. So everyone that can upload their machine learning model there needs to provide some information. But currently it's just suggestion. We try to do empirical research, looking into the data that's really being provided, accompanying this machine learning model, and we found that it's really sparse. Just gets information about who is creating that, what is the time of creation. If you ask about the evaluation processes, how this model is being evaluated, currently it's I don't know, probably about 20-30% of the models being uploaded there have this information. So I think it's more, I mean, we have to be more tighter in the sense of regulation, otherwise it's hard. Thank you.
Just was one remark, and that was a question to one of the previous questions about the group at VWGÖ, and the wrong answer. In some way, it is a questionable, was it the wrong answer? Because ChatGPT has to evaluate or have even the sources for the right answers. And like this group is perhaps not, it's quite a new group, so it was not evaluated at the time, perhaps it is not even in the database, something like this. So these are things which are there, but there is another question. The knowledge base is one of the most important sources. And now we have also sources like fake news and all these kind of things. So it is not very surprising that many answers are wrong. So this is normal. That's why I think one of the most important issues is to be explainable, and I think there are many steps of the European Union in this direction already. Explainability is important. We know from the areas of medicine, for example, that of course most AI programs are much better than specialists. Of course, why? Because of the profound sources of millions and millions of images. The best specialist cannot have it during his lifetime. This is quite true. So what we need is something like to have explainability. The other thing is we shouldn't overrate human intelligence. Why? First, we are very diverse anyway, but why are we, what we say in German, masculine? It is just a product of evolution. So we are also making a lot of mistakes. And we have just to look to the internet how it looks like. So the average human is perhaps not to say das masculine.
Okay, thank you. By the way, I'm Johannes, professor also from computer science. Okay, this was almost a final statement to this part. Well, I think probably the time is over, yeah. So I thank the speakers for participating and for sharing.